All right, let's continue on with part two of our lecture on integrals. And this time we're going to talk about constants of integration, which I'll explain in a second. And then just going to do some more examples. This should be a fairly short section, a fairly short part of this four-part lecture. So let's go ahead and get right in. When I talk about this constant of integration, I'm going to actually pose this sort of in the sense of a question here. So I want to know which of the following are true statements here. So I've got these four integrals, and what you'll notice is that they're always the integral of 2x dx. Again, I haven't explained that dx yet, but don't worry about that for now. So we're taking the integral of 2x in all these cases, but what you're noticing is I actually have four different answers here. Let me highlight these for us. And then I want to ask the question, which of these are true statements? And sort of think about that while I'm highlighting these. You know, of these, I've got these four integrals. Are all of these true? Are none of these true? Are one of them true? And so let's actually dive right into this. So this first one here, this seems very natural. We saw this example last time. We saw that, hey, I've got 2x. If I take an interval of that, I get x squared. We can confirm that by sort of thinking backwards. We can say, hey, if I have x squared and I take a derivative of it, I should get 2x, right? And so that means that flipping that sentence, I get the integral of 2x is going to be x squared. Well, so this is obviously true. So let's go ahead and put a big check mark next to that. That's good. That is true right there. But now let's look at these others. Let's look at this guy in particular, x squared plus 1. And so it seems like if this is true, then this can't be, because you might say, hey, well, if the integral of 2x is x squared, I can't have a different answer. It's got to just be x squared. So it's not going to be x squared plus 1 or any of these others. That's actually faulty thinking. Probably for once in our lives, we can have multiple answers to a math problem. And this is probably the only scenario that I can think of where that happens. But it turns out that all of these are actually correct answers. They are actually true statements. So let me explain. We're going to think backwards here on all of these, just like we've been doing with integrals. So we're going to take this supposed answer, and we're going to say, all right, if we take a derivative of it, what do I get? And if you take a derivative of this, you should just get 2x. We do our power rule here, which gives us 2x, but this is a constant. And so when I take a derivative of it, it goes to 0. And so I just get my derivative of this being 2x, which means that the integral of 2x is in fact x squared plus 1. And it's also x squared minus 4. It's also x squared plus e, because all of these are just constants that I'm either adding or subtracting. So when I think in the reverse and I take a derivative of these guys, I end up just sort of getting rid of that constant, because when we take a derivative of a constant, it goes to 0. So it turns out, in fact, that all of these are true statements here. And so this lends us to the question of, well, how do I actually give an answer then? How do I actually state, my final answer? When every time you give me an integral, there's all of these answers. And heck, I mean, you could write x squared plus 2, x squared plus 3, x squared plus 4, I mean, you could just keep going forever, right? There's an infinite number of answers. So how do we actually write this out? Well, what we write is we just sort of add a c, just a lowercase c, and we say, hey, that's a constant. It works. And so using this notation that we've seen last time, if I take the integral of a function, that's going to give me some answer. I'll have an answer, right? Maybe this is a 2x and this is an x squared. But what it's saying now is that I can just add c, and I should add c, because in reality, the integral of 2x, it's not just x squared. It's x squared plus any number of things, any number that I want. I could add a 1, I could add a 7, I could add a -2, I could add anything. I could add pi if I wanted. I could also add 0, and then I would just be left with x squared. But any of those works, so my answer has to be this guy, all said and done. So basically, you can add a constant to the answers for these integrals, and it still works out. But let me emphasize, you should be doing that, because if you just write this that I've boxed in the red, if you don't include that plus C, that's not correct because there are other answers there that work. So got to make sure that you put your plus C there. I want to make one thing very clear. Here I've added an E, and this is where things get a little weird. A lot of times when people see the letter E, they think, oh, that's a variable. It's, it's like an X or something like that. Well, remember that E is like pi for mathematicians. Whenever you see an E, that's that 2.71828, and then it just keeps going on. I forget exactly what after that. But E is that 2.71-ish value. It's just like it's the same type of thing as pi, but obviously because pi is a symbol that we're used to seeing as opposed to a letter like E, people tend not to confuse pi, but just be careful. E is a letter which stands for a number. It's not a variable. So C here, sometimes just when you have C and E next to each other, it can confuse people, but C here just stands for any sort of constant. Let me also be clear. Some people will put a capital C. I don't really care what you do. I'll put a lowercase c generally. It's just for my own reasons. It's not really that important, but lowercase c, capital C, either is fine, but we should put them there. So moving on to just some examples, and we're going to remember in these that we want to put our plus C here. So let's actually break these down step by step. So we'll go ahead, and I'm not going to bother manually copying or automatically copying those. I'm just going to write these out manually. So we've got 2x plus 5. And one thing that I do want to make note here, writing that integral like this is a little bit weird because I don't have parentheses. Some people may interpret this as like a 5dx as one thing. It's not, but just to be safe and careful, we like to put parentheses around that. Just to be careful, just to really indicate, hey, this is what we're taking a derivative of. And again, I know I haven't talked about this dx yet, but don't worry, it needs to be there. It's sort of like a, hey, I've got the function that I'm taking an integral of wrapped between the integral sign and the dx. And we'll get more into what that means later. But for now, we've got this. And I just want to do this by inspection. So when I look at this, I have a thought of, hey, we have these rules with derivatives, right? So we have these rules that say that if I have if I'm taking a derivative of something that's added together, two parts that are added together, I can just take a derivative of each of them separately and then add them together. And actually the same thing works for integrals, but don't just take my word for it. Let's just try it and see what happens. So we've seen this example where the integral of 2x is x squared multiple times. Let's just try now, what's the integral of 5? Well, with some thought, you might recognize that, hey, if I have 5x and I take a derivative of that, that's going to give me 5. So going backwards now, the integral of 5 is 5x. We've got a supposed answer here. Let's check it. If I take a derivative of this, you in fact should see that you get 2x plus 5. That matches that. Yay, we're good. But we're not done here because this, while it is a correct answer, it is not all of the correct answers. We have to put that plus C in there. Otherwise, otherwise it just doesn't work. Or, that's just the x squared plus 5. While it is correct, it's not all of your answers. So you got to make sure that you're putting that plus C there. All right, let's go ahead and do one of the other examples on here. So -1 over x squared. This is kind of a hard one for me to explain without actually showing you the rules of integrals, sort of the power rule for integrals. But thinking about this and maybe just, sort of banging your head against a wall for a bit and trying to just come up with the answer, you should see that if you have 1 over x, that if you take a derivative of 1 over x, you should get -1 over x squared. Let me show that work off to the side right here. So d dx of 1 over x is equal to, well, before even taking a derivative, I can just write this as x to the -1. And so now when I take my derivative and I use my power rule, I have to subtract 1, or excuse me, I have to drop that power down. so that -1. And then I have to subtract 1 from that power. So when I subtract 1 from -1, I get -2. This just simplifies to -1 over x squared. So we're seeing here that the derivative of 1 over x is -1 over x squared. So now flip that statement. That means the integral of -1 over x squared is 1 over x. But don't forget, plus c. There we go. All right. Let's go ahead and do another example here. So we've got e to the 7x dx. And again, just sort of guessing and checking, I might be inclined to just write e to the 7x. And then if you check that, what you're going to notice is that it doesn't quite work. If I take a derivative of e to the 7x, and I won't explicitly show all this chain rule, but do know that the chain rule is there, I should get 7e to the 7x. And so it seems to me like I've got an extra 7 here that I don't want, right? I'm trying to find something that when I take a derivative of it, I get e to the 7x. And this doesn't work. It gives me an extra sort of 7 here. So what if I did this? What if I just kind of moved all of this over a little bit? And what if I just added in a 1/7 right in there? Well, that would mean that I would just kind of add a 1/7 right in here, right, by that constant property of derivatives. And oh, look, the 7's cancel. I just get e to the 7x. And so, in fact, I want to put a 1/7 out front here and a plus c. Don't ever forget that plus c. And so taking this right here, you can see the work that I showed right here. When I take a derivative of this, I get e to the 7x. Yay, we're good, we're happy. All right, so now let's go ahead and look at the fourth example here. So 5 to the x dx. And this one we got to be careful about because this is an exponential, but it's not base e. So e is not our base. And in fact, our base is 5 here. So let's just do this. Let's start off with this idea that, all right, it's an exponential. Let's try just copying it down, because that's what we tend to do with derivatives of exponentials. We just kind of copy down what's there. So let's just put 5 to the x. Well, if we take a derivative, so now I'm going to check my supposed guess, my guess here. If I take a derivative of 5 to the x, I get 5 to the x ln of 5. And that is not just 5 to the x. We have an extra ln of 5. So let's take a page out of our book from what we did up here and just kind of throw a 1 over 7 in here. Let's just throw a 1 over ln of 5 in here. And it turns out that if you do that, let's not do that, what I just did. So let's just divide by an ln of 5, right? Before I multiplied by 1 over 7, that's the same as dividing by 7. I can, here I'm just dividing by ln of 5. Well, when I do that, I end up just taking this guy, constant property, I just divide by ln of 5. And oh, look, these cancel, and I just get my 5 to the x. And so turns out here, I just want to take this and I want to divide by ln of 5 plus c. And there you go. You can now check this, and I now have the work shown right here. If you take a derivative of 5 to the x ln of 5, you just get 5 to the x. And that's exactly what we're seeing right there, what we're hoping for right there. And we have confirmation of our answer. And yeah, I know this is kind of weird, sort of this strategy of how we're going through these. It really, at this point, it's really just a guess and check, and just kind of try them out and just hope it works and edit your answer accordingly. So let's get into the last two examples here. So we're going to have integral of 4 over x dx. And I see that over x here. So this, to me, it kind of looks like a 1 over x dx, which we actually saw in the last lecture. This was ln of x. So why don't we try this? we have that 4 over x there. Well, let's again think back to when we take a derivative, we have derivative properties that tell us that, hey, we can kind of just ignore that constant. We can bring it out front and just multiply it back in at the end. So let's do this. Let's just forget about the 4 for a second. Just pretend it's a 1. Well, that means that my answer is ln of x. But now let's remember that there's a 4 there. So let's just try multiplying it by 4. And if you check this, you should in fact see, hey, d dx of 4 ln of x, I'll explicitly show that constant property. I can pull that 4 out right there. Now the derivative of ln of x is just 1 over x, and this just gives me, simplifying, just 4 over x. And so, ta-da, we've got it. The derivative of this is that. So the integral of 4 over x is 4 ln of x. Then, don't forget, plus c. Thought you might catch me there, but I never forget. That's not true. I probably forget sometimes, but don't forget that plus c. It is important. So now let's do our last example, 4 over x minus 3 dx. And when I see this, it pretty much just looks like the same thing as what we had before. So really, I'm going to have my 4 out front. I'm going to have my ln. But the difference here is that it's not just an x, it's an x minus 3. Then my plus c. And in the same, pretty much the same exact work as here, you can take a derivative of this and you will get that. I just want to make it clear that here we have an x minus 3, here we have an x, and it didn't really change things there. That is actually, the fact that this didn't change a lot, we actually kind of got lucky. That's the nature of how I decided to write the problem. Here's what I will say. If I put a 2 right there, this problem changes dramatically. It does not look like that would make this much harder, but it does. It changed the problem wildly, and there's actually a whole other lecture for things of that nature. And so we won't get into that yet. So this, we just kind of got lucky that it was that simple. But if even just doing something like putting a 2 here makes it way harder. So don't just assume that, oh, it looks like what we did before, I can just copy it in, but we'll get into that later. For now, that's just these examples here. I'll actually go ahead and leave us with a little anecdote, with a little story about plus C, to hopefully give the importance of plus C. So when I took calculus, I actually, when I first started learning integrals, sort of the corresponding exam that you would have on this material, I took an exam, and the exam was very straightforward. It was just 10 integrals. They looked like this. There were 10 of them, and it just said, do them. There you go. And what my teacher ended up doing when she graded them was she gave 1 point for this part of the answer, and she gave 1 point for the C. And so I actually had 2 friends. One of them, or they both got 50% on the exam. One person got all of these correct, but never wrote plus C. So he got a 1 out of 2 on every integral, on every problem, because he didn't write plus C. The other friend who got 50% just missed all of these completely, just did them all wrong, but wrote plus C. And so, I don't know, I find that kind of a little funny anecdote there, just showing the importance that, hey, the plus C is important there. You got to make sure to write that. I'm not going to be as drastic as, hey, 50%, 1 and 1, but be careful there. It is important. There is a reason that it's there. And so it is important to write that down. We'll go ahead and leave that there. And that'll be part 2 of this 4-part integral lecture.